Hi, welcome, and thank you for joining us at today's session on Patient Flow and Digital Command Center, brought to you by IBM and Potentia Analytics. This next slide is the agenda for today's session. We'll be doing introductions, defining the command center, talking about the journey from data to wisdom, and the big problem, which is demand capacity mismatch, how machines can help, and flow variability. We'll also be discussing IBM's and Potentia Analytics Command Center solution with a framework overview, key components overview, command center functionality, technology infrastructure, computer-assisted decisions, and then we'll talk about the journey with standing up a command center, sample of flow and data walls, and a case study. And then we'll also be talking to you about the future. Let me introduce you to your speakers for today. This is Paula Rowe. She's an operational excellence practice leader with Simpler Consulting and IBM Watson Health. Paula has over 25 years of leadership experience in healthcare. She's a frequent contributor to healthcare industry publications and a subject matter expert on the role of hospital administrators, physicians, and staffs in transforming their culture. Paula's passion is sharing her lean expertise and teaching healthcare leaders and clinicians how to align process improvement efforts to organizational strategy and how to implement digital solutions, including advanced analytics, real-time data, AI, and robust visual management to improve flow and optimize hospital resources. Currently, Paula is supporting teams in the US, Ireland, and Saudi Arabia in their traditional and digital lean transformations. Paula will be sharing the stage today with Dr. Sean Bazorgazad. He is the CEO and co-founder of Potentia Analytics. Sean comes from a diverse background, including emergency medicine, data science, healthcare leadership, and software development. He operates at the nexus of computer science and medicine. He leads a team of software engineers and data scientists dedicated to improving healthcare operations through leveraging artificial intelligence, machine learning, and the latest available data science technology. Sean and his team view the current pain points in healthcare as the fuel that drive their innovation. When building solutions, Sean and his team strongly believe in empowering those who work at the front lines of healthcare. Serving the server is a necessary part of improving the quality of care for patients. He works hard to facilitate the interface between the worlds of healthcare and data science.
Hello, my name is Paula. Over the next 30 minutes, Sean and I are going to share what we believe is the best known way to leverage technology to optimize the patient care journey. We refer to this approach as the Patient Flow and Digital Command Center. The goals of the Patient Flow and Digital Command Center are to monitor patient flow throughout the hospital to reduce waste and waiting. We also aim to improve flow by identifying delays and engaging the necessary individuals and teams to take actions. We aim to expedite patient access to care, optimize staffing to demand, facilitate communications and collaboration among all departments, and optimize the hospital's operations in an efficient and effective way to reduce cost and improve service delivery.
The pyramid at the core of this slide represents different stages of transformation of data on the path to achieving the highest state of usefulness. Central to our project is facilitating this journey for our healthcare data. This journey starts with unstructured bits of information and ends in actionable insights labeled as wisdom at the top of this pyramid. In the context of our presentation today, it is imperative that we facilitate this journey for all healthcare data if we are to achieve operational excellence. The journey from data to knowledge is usually concerned with the past, and the journey from knowledge to wisdom is usually geared towards improving the future. As the data moves up the pyramid, our understanding increases and the context becomes more clear. Every healthcare facility deserves to have their data reach its highest state of usefulness.
In our experience, the biggest problem affecting operational efficiency in healthcare is demand capacity mismatch. Matching capacity with demand is a delicate balancing act. When demand exceeds capacity, we have bottlenecks, increased safety risks, and decreased quality of care. When our capacity exceeds demand, we have increased waste and high cost. So what does demand-capacity mismatch mean for veterans and those who care for them? Well, for our veterans, it results in prolonged waiting times, decreased access to valuable services, delayed diagnoses, delayed care, and in some cases, suboptimal outcomes. It also can result in healthcare provider burnout and increased waste and frustration in the system. So why is demand-capacity mismatch so prevalent in healthcare today? Well, we've accepted the fact that a lot of this variability is not known ahead of time, but actually that's simply not true. Our data has demonstrated that we know who's coming and what they will need, we just don't know their names.
As Paula mentioned in the previous slide, we know a lot about our patients before they walk through our door. You may ask, how good are we at this prediction? The answer is, in our experience, using a form of artificial intelligence called deep learning, and taking into account all the factors that may affect the flow in each specific facility, we have achieved accuracy levels of greater than 80%. We can predict who's coming, when, and with what needs. The graph shown here is a depiction of accuracy of prediction of patient flow, shown as patients per hour with the yellow line, overlaid on the actual flow shown with the blue line at a healthcare facility that serves approximately 100,000 patients per year. For most parts, there is great overlay of peaks and troughs.
This is a visual overview of our digital command center framework. The circle represents the digital command center. The icons above represent various departments and services that are in scope for the digital command center. This is not an all-inclusive list, as we would also include support systems such as human resources and supply chain management. The box to the left of the circle represents the various data inputs, data from the electronic medical record, staffing and scheduling systems, and also external factors such as weather, disease migration, and local events all feed into the digital command center. The box to the right represents the projected outcomes of all the activities from within the digital command center. And the boxes below represent the must-have, can't-fail elements of the business management system to assure a successful implementation of the patient flow digital command center. It all starts with a future state and a vision that's aligned to the overarching strategy of the organization. Second, we use the data insights to optimize the process of care delivery and match capacity to demand. Once optimized, we enhance the ongoing daily management of the system to forever improve and eliminate bottlenecks. Finally, we align command center governance. Leadership guru John Maxwell often says, everything rises and falls on leadership, and this is such a powerful and true statement. It really doesn't matter if you have the best technology tools to visualize and alert staff to areas that need attention. If top leadership is not fully committed to the deployment of the digital command center and its associated standard work to be effective, the results will not be achieved. The digital command center construct is made up of the following technology components: predictive modeling, alerts and notifications when a bottleneck is anticipated or detected, real-time monitoring and visibility of staffing and other vital resources such as beds and ventilators, machine learning and AI to predict outcomes, benefits tracking and continuous improvement capability, and the ability to create what-if scenarios with known results.
This slide represents the infrastructure of a typical command center. The large rectangular box on the bottom represents all systems of record providing data input. The list shown here is only an example and there are no limits to how many sources of data can provide input. The data moves from the system of record to the initial layer, which is made up of an interface server and a messaging data store. From there, the data moves to an application data store, which feeds a platform API that can then be used by the patient flow command center, a communication application such as a mobile app for notifications and alerts, and a data analytics platform for performing AI. The insights generated by the AI are then fed back to the communication platform through the API layer. What does a patient flow command center do for me? Please keep in mind that the list presented here is only an example of some of the capabilities of a command center. By no means it's meant to be an exhaustive list. A command center aggregates all the information that is out there that you need to know in order to manage the performance of your healthcare system. A command center puts your finger on the pulse of your healthcare system by examining in real time all the internal and external signals affecting your flow. A command center acts as an early warning system that can issue alerts before problems hit. A command center has a simulation engine that allows you to fast forward the current conditions and identify future bottlenecks. A command center has an AI-powered optimization engine that helps you search for the best deployment of your resources in order to alleviate the bottlenecks before they occur. A command center improves the quality of your decisions by giving you actionable insights. What role does technology play in the operation of a command center? Technology can help us see our system in the context of the greater society and the environment by connecting different sources of data. When we see our system in context, we understand how our system interacts with its environment. A good example of the interaction between a healthcare system and its environment would be the way a disease outbreak affects the operations of a healthcare facility. COVID-19 is a good example. Influenza outbreak is another good example. Every year, influenza increases the load on our healthcare system, and knowing the nature of this interaction helps us better plan and prepare for the change in demand. Technology speeds up the transformation of data to wisdom. Going from data to information to knowledge to actionable insights is greatly accelerated by technology. Technology helps us predict the demand on our system and optimizes the utilization of our precious healthcare resources. Technology can help us with the delivery of insights to the right people at the right time, and most of that process can be automated. Technology can receive, parallel process, and store high volumes of data. At this time, a good question would be, do we have to rely on computers to assist with these tasks? The answer is yes. The sheer volume of data and the need for processing speed makes these tasks very difficult for a human. As you can see here, the basic operational speed of a human brain and a machine are very different. So is the precision. Also, the memory of a human mind is limited, but memory of machines are unlimited. So the conclusion is, appropriately used machines can significantly augment the depth and the speed of the decisions we make, and therefore improve the quality of our decisions.
We utilize an agile approach to standing up a patient flow command center. In a short period of time, we build a small part of the system, a working element to get quick results. And then we continue creating value by adding subsequent use cases. Developing incrementally through short iteration allows for faster cycles of learning and built-in quality. It all starts with a comprehensive diagnostic of the entire ecosystem, including the people, the processes, and the technology. We determine where to land and expand with alignment with the organizational strategy and key performance indicators. We establish benchmarks and transformational goals. We connect real-time data feeds from all sources of truth. We work with teams to determine alert protocols and escalations that drive human and system performance. We set up the visual monitoring in the command center itself. We then apply machine learning algorithms to several years of historical data to predict flows. We train and support staff to launch system alerts and assure triggers are set correctly to prevent alarm fatigue and assure the right people are alerted at the right time. We integrate the performance improvements methodology to drive continuous improvement of the entire system.
This slide represents a sample flow pattern extracted from the data of a healthcare facility in southwestern US. The green dot represents the point of entry, the blue dots represent possible different exits, and the yellow dots represent stations in which some service is provided to the patient. Any resistance in the patient's journey will negatively affect the patient experience and cause delay in care. Removing the resistance to the flow of patients is the goal of a command center. Determining the speed of service and coordinating allocation of resources to each station is the job of a command center. This task is quite complex and takes into account multiple different factors. This work is best done by an AI algorithm. This slide represents a sample command center data wall. The specific dashboard shown here is the patient journey through the emergency department. The stations portrayed have built-in color-coded current state, black showing normal operations, yellow showing cautionary status, and red indicating an alert status. These walls in the command center are designed to visually demonstrate the current status of the department. This data wall can be used to display imaging turnaround time in a typical inpatient or emergency department. The left upper corner shows active patient orders in cautionary and/or alarm status by modality. The right upper corner shows all open encounters and a breakdown of the length of the procedure and the alert status. The left lower corner shows the number of tests that have met an alarm status in the last 30 cases. And the right lower corner shows the most common causes for the delay in care and the most common causes for issuance of alerts to caretakers. This slide is an example of a data visualization of a patient to provider ratio in a given hospital. Each square represents a 1-hour period in a given day. From the left to right, the start time is midnight and the end time is 11 p.m. on the same day. On the left side, you can see the days of the month from the 1st of the month to the 29th. This is for January 2018. Red squares are the hours in which the ratio of patients to providers are the highest in a 24-hour period, typically over 14 patients per hour. The most consistent pattern in this slide is the high ratio of active patients to providers between 1 a.m. and 6 a.m. This is a very good example of resource allocation mismatch in a given emergency room. This slide shows a sample data visualization of patients leaving without treatment in the emergency room that was shown in the previous slide. It's for the same period of time, January 2018. The red squares represent the areas of the highest number of patients leaving without care, usually more than 7 per hour. These areas correspond with high patient to provider ratios demonstrated in the previous slide. One of the objectives of any command center is to alleviate these resource planning errors. Now it's time for us to present to you a case study. The case study that we have chosen is an emergency department case study, and it's a length of stay optimization in an academic emergency department with an annual volume of 68,000 visits. The two main resources optimized were nursing and provider. The changes were recommended by an AI search algorithm. The changes were kept budget neutral, and the overall impact of 47,000 patient care hours yearly. Length of stay optimization. This length of stay reduction case study achieved a 0.68 hours per patient visit reduction in the length of stay by reallocating resources as per recommendations of our AI algorithm. Because this was a budget neutral case, we had to take resources from times where the demand on the system was light and allocate them to times when the demand on the system was high. The overall potential impact was 47,000 patient care hours per year, and if we were to assume an estimated value of $500 per patient care hour, the total value for this facility would have been $23 million. This slide represents nurse shift distribution pre and post optimization. The pre-optimization shift distribution is shown with the blue line. As you can see, the number of nurses in each hour during the days of the week are shown on the vertical axis, and the days of the week are shown on the horizontal axis. The number of nurses fluctuates from 11 per hour to 32 per hour. As you can see in this slide, the maximum nurses recommended by the software at this time were 28. However, historically 32 nurses were scheduled to work. On the same token, in different parts of the week, such as Sunday, early hours of morning, the software recommended to keep the number of nurses higher than we historically had scheduled for. So our AI algorithm recommended keeping the number of nurses during this period at 24 compared to the historical 10. So the whole purpose of this optimization is to take resources from areas where there is no need and allocate them to areas of a higher need. This is a similar slide showing provider shift optimization depicted by the yellow line and the original shifts depicted by the blue line. As you can see, during the early hours of Tuesday, our AI algorithm recommends keeping the number of physicians at 7. However, historically, this facility has scheduled only 2. As you can see, this will create a significant mismatch, resulting in patients leaving without care and increased risk and decreased quality for the patients in the emergency department at that time.
A patient flow command center utilizes predictive analytics, AI, and simulation and optimization engines to answer the 5 questions of flow. Who is coming? When are they coming? What are they going to need? Do we have what they need? And what are we going to do if we don't have what they need? By answering these 5 questions of flow, we make any medical center or department better every single day. We have the technology, it's available, and we can do this. Let's leverage data science to take care of our nation's heroes, our veterans.